In this video, we'll discuss the topic 6.4, which is rabbits versus sheep. Okay, so this is one population growth model. Okay, so which is known as Lotka-Volterra model of competition. Okay, so it's not a predator-prey model. So here actually the species which has been taken are, one is rabbit and another one is sheep. Okay, so here it's actually it's not like one will eat other. Okay, it is more like it has same source or same food like grass. Okay, and that's limited, and within the limited food supply, they have to compete each other. Okay, and therefore at that time how the population is going to grow for rabbit and sheep. So that's what we are going to identify. Okay, so now for this so in the mathematical form, this equation has been written like this, and I leave the formation of this equation as an exercise. Okay, so maybe if you read this you will have an understanding about how we have obtained this equations. Okay, where in this equation x represents the population of rabbits and y represents the population of sheep. Okay, and we know that we are discussing about the population, so both these variables has to be a positive one. Okay, so now let's start analyzing it. The first thing is, let's identify the fixed point. Okay, so what are the fixed points? So okay, the fixed point, the x dot has to go to 0 and y dot has to go to 0, right? So we know x dot will go to 0 when x is equal to 0, or whatever inside this bracket goes to 0. Okay, so the x is equal to 0 is one straight line in the xy axis, and this represents another straight line. Okay, similarly y dot will go to 0 when y is equal to 0, or this one goes to 0. Okay, so now in order to identify the fixed point, we could have so from this we obtain two straight lines, right? And if any of these two straight lines intersect any of these two straight lines, then that point will be a fixed point. For example, x is equal to 0 is one line, and y is equal to 0 is another line. Okay, those two will intersect at 0, 0. So that's one fixed point. Okay, and when x is equal to 0 and this one, okay, those two intersect at a point which is 0, 2, and y is equal to 0 and this line will intersect a point which is 3, 0. And the fourth point is this line and this line will intersect, and that's the fourth point, which is 1, 1. So these are the four fixed points. Okay, now let's classify the fixed points. Okay, and if we to classify the fixed point, we need to calculate the Jacobian, and this is what the Jacobian matrix we have. Okay, now let's say what is the Jacobian for this fixed point 0, 0, and that gives us this one, and from this we could say that it's going to be an unstable node. Okay, it's going to be unstable node. I mean we could calculate just with an eigenvalues or with trace and determinant. Okay, so that's up to you. So either case you will identify that it's going to be an unstable node. Okay, Okay, so that's unstable node, and so now we have the eigenvalues, and for an eigenvalue lambda equal to 2, if we check the eigenvector, which is 0, 1, okay, so that's 0, 1, which means that will be the initial direction of the manifold, or one of the trajectory, okay. But anyway, we will discuss about that later. So one fixed point is going to be an unstable node, okay. So, and also from the eigenvector we were able to identify that maybe the trajectories which comes out of this, so it will come out because it's an unstable, and it will come out in this particular direction, okay. So that's what we have understood. Okay, now the other thing is the other fixed point, which is 0, 2, okay, and in 0, 2, so some let me finish this one. So some okay, one of the eigenvector is 0, 1, and another eigenvector is 1, 0. So some trajectories will go in this direction, and the other trajectory will go in this direction along the x-axis, 1, 0, okay. So those are the two lines which will emerge out, okay. And then if we see the next fixed point, which is 0, 2, and we are able to understand that the eigenvalues are -1 and -2. The eigenvalues are -1 and -2, then it is going to be like a stable fixed point, because both the eigenvalues are negative, okay. So in the picture, okay, the point is going to be here, and it's going to be attracted, okay, attracted all the trajectories near to it, and the dominating direction can be identified using the eigenvector, okay. Okay, so similarly, if we do for the other fixed point, we will get, this is the A matrix, and once again we are having eigenvalues are negative. So this is also a stable fixed point, okay. And so this is the point, and you could say that everything is going to get attracted, okay. And if we see, mainly this is going to have, I mean, initially there will be a trajectory which directly approaches this one, will have this direction, okay. So now the fourth point, which is 1, 1, okay, which is somewhere here, and if we calculate the Jacobian matrix or A matrix, then what we are having is trace is negative and determinant is negative. So once we see the determinant is negative, we can easily see that it's a saddle point, okay. So if it's a saddle point, then it's going to have, in one direction it's going to have an attraction, and in another direction it's going to have a repulsion. So there will be one an unstable manifold, and there will be one stable manifold, okay. And in which direction immediately those manifolds are going to emerge, that we can identify using eigenvalue analysis, okay. So and from that we could understand that this is going to be the directions. Okay, now now let's put this picture, this and this together. Okay, so if we put that, this is what we will get. Okay, so now from this, what can we say? So from this, maybe it's, so let's focus on this one. Okay, so maybe this will come out of somewhere and then approaches towards this point. Okay, it cannot emerge out of this point or anywhere, any other point. Probably it might be started from this point and then it might approach this one. Okay, so there might be a trajectory which starts from this point, okay, and end at this point. Okay, there will be some trajectory. Okay, and then similarly, so it's so it may start somewhere from very large, very far from here, and it will come towards this point. Okay, so that will be our unstable manifold. Okay, then let's look at this trajectory which emerge out of this one, which is a stable manifold. So it will, sorry, this is an unstable manifold, this is the stable one, right? Yeah, so this unstable manifold, actually it will emerge out of this saddle point, and probably it will be attracted towards this fixed point. Okay, which means there will be a trajectory which connects this point and this point. Similarly, there will be another trajectory which connects this point and this point. Okay, so we do not know exactly what is that trajectory line, but we can qualitatively understand that there will be a trajectory. Okay, so from that we could by connecting those trajectories, we could have a little better understanding about this system, so which is going to be like this. Okay, and also yes, there will be some trajectory which starts from here. If it's not going to get attracted over here, it will get attracted over here. Okay, so that is this curve, and similarly we will have such a curve between this point and this point as well. Okay, so which is this curve. Okay, so right now we have somewhat a better picture. Okay, so from this picture, what can I say? What about the other fixed points? Maybe what if I start from here? Maybe initially it will go like this, and then it will come back and it will get attracted. Okay, what if it starts from somewhere here? It may go like this, and then it will once again attracted toward this point. How about here? It will go like this, but it will not attract it towards this point. Okay, it will go like this and it will come back, it will go towards this fixed point. Okay, so from this what I can understand is, if the initial condition is this side of this stable manifold, okay, this is going to be the attractor. At the same time, if this is the fixed point, sorry, this is the initial condition, then this is going to be the attractor. Okay, so that's only very rare case where a fixed point, an initial condition which is along this line, okay, which is along this stable manifold, which will eventually end up at this point, which is 1, 1. Okay, so what are these fixed points mean to us? So this fixed point, which is 0 comma 0, which means there are no rabbits as well as sheep. Okay, and this point tells us there are only rabbits and no sheep, and here it tells there are only sheep and no rabbit, and here both are existing at the same population. Okay, so that's what this particular point tells us. Even a slight deviation from here will either vanish the entire sheep or entire rabbit. Okay, so right, that's what we have to understand. Okay, so yeah, with the additional curves we could identify the face portrait. Okay, and then and this region is also known as basin for 3 comma 0, and this region is known as basin for 0 comma 2. I mean, the reason is because if we have an initial condition, it starts in this basin, it will be attracted towards this point. Okay, which means it will vanish all the sheep and it will end up with only rabbits. Okay, and at the same time, if we choose here, then this is going to be the attractor. Okay, so yeah, so that's an example of on population growth which uses 2D flow system. Okay, which is being represented using 2D flow system. Okay, so and this stable manifold, which is known as which is also known as basin boundary. Okay, and also this is also known as separatrix. Okay, so those are some names. Okay, and you could easily see that that identifying that line is very, very important, because that is going to say that what is going to be the fate of the system, right? So that's very important. Okay, fine. So with that we'll conclude this example, and we'll see some more topics in the next lecture. Thank you.